James Webb has not photographed the first star. It has found something almost stranger. It has found light so early in the universe that the darkness before it now feels shorter, busier, and less empty than many astronomers once expected. There are galaxies shining only a few 100 million years after the beginning. There is oxygen in one of the most distant galaxies ever confirmed. There are tiny red smudges in deep fields that should have been faint, rare, and simple, but instead look bright, compact, and already changed by stars that lived before them. That is the mystery tonight. Not the end of the lights, as we followed last time, but the first one. Before the sun, before the Milky Way, before planets, moons, oceans, or any sky with constellations. There was a universe with matter, gravity, and a cooling afterglow, but no local fires, no sunrise anywhere, no starlight crossing a room, no shadow, because there was no lamp to cast one. Then something in the dark collapsed. A cloud fell into itself. Hydrogen became heat. Heat became fusion. And somewhere, in a place with no name and no witness, the first star turned on. Tonight we follow that light from the oldest darkness to the edge of what Webb can see, and to the evidence that the first cosmic morning may have arrived faster than the old maps allowed. The question is simple. Where did the first light come from, and why does it look as if the universe learned to shine too soon? In the last journey we went forward. We followed the universe through rooms so old that stars had become rare, then gone, then remembered only by the small things they had once made possible. At the end of that road, the dark was an ending. Tonight we turn around. Because there was another dark before the stars, and that dark was not an ending at all. It was a beginning. The strange part is that these two darknesses can feel similar from far away. The far future dark has almost no lamps left. The early dark had none yet. One is an old room after the fire has gone out. The other is a young room before the fire has been built. If you only say the universe was dark, you miss the difference. In the far future, the universe is tired. In the beginning, it is waiting. The early universe was not empty. It was not a black stage with nothing on it. It held hydrogen, helium, dark matter, radiation, and the seeds of every later galaxy. It held small, uneven places in the density of matter. It held gravity, already patient, already choosing where things would fall. But it did not yet hold stars. That is the key. A dark universe is not the same thing as a simple one. The young cosmos had already survived its first violent moments. It had expanded from a hot, dense beginning. It had made the lightest elements, mostly hydrogen and helium, with tiny traces of lithium and beryllium. It had cooled from a furnace into something that could become structure. But for a long time, nothing inside it could shine the way stars shine. There were no galaxies to cross a deep field. There were no spiral arms. No white dwarf embers. No red giants. No blue stars burning through nebulae. No planets receiving morning. The familiar universe had not begun to look familiar. A person standing there, if a person could stand there, would not see a black sky filled with stars, There would be no ground, no air, no eyes, and no body. But even as a thought experiment, the scene matters. There would be no constellations because there were no stars to connect. There would be no moonlight because there were no moons. There would be no sunrise because there were no suns. There was only matter spread across a growing universe waiting for gravity to gather it. This is why Et5 belongs after the last light journey. The end of stars asks what remains after light has done everything it can do. The beginning asks what had to happen before light could do anything at all. And the answer begins not with a telescope, but with a small imbalance. The early universe was almost smooth, but not perfectly smooth. That almost is the reason anything exists. If matter had been spread with perfect evenness, every place would have pulled every other place the same way. Nothing would have had a head start. Nothing would have become a centre. No cloud would have fallen faster than another cloud. But the universe was not perfectly even. Some regions were slightly denser. That was enough. Gravity does not need a dramatic beginning. It only needs a difference. That difference can be almost unimaginably small and still matter later. A tiny excess of matter does not look like a galaxy at first. It does not even look like a cloud with edges. It is only a place where the pull is slightly stronger than the pull around it. But the universe is patient, and over long stretches of time, small advantages become structures. This is one reason the early dark should not be pictured as dead. It was full of unfinished shapes. It had no stars to reveal those shapes yet, but the shapes were beginning. The dark was not a curtain over nothing. It was a curtain over work. A region with a little more matter pulls a little more strongly. Because it pulls more strongly, more matter falls toward it. Because more matter falls toward it, it becomes denser still. The process is quiet, but it is not weak. It is the same basic patience that later builds galaxies, stars, planets, and clusters of galaxies. The Dark Ages were not an idle pause. They were the universe gathering itself. In the darkness, matter was learning where to go. Invisible dark matter formed the first deep valleys. Ordinary gas, mostly hydrogen and helium, followed those valleys. The gas did not know it was moving toward light. It only followed gravity down. This is the first soft, open loop of the episode. Before the first star could shine, the universe had to build a place where a star was possible. It had to make a dark room, dense enough to become bright. And to understand that room, we first have to visit the oldest light we can still see, because the story of first starlight begins with a different glow, a glow that came before stars and still surrounds us tonight. There is a kind of light, older than every star. It is not starlight. It did not come from a sun. It came from a whole young universe-changing state. Today, astronomers call it the cosmic microwave background. It is the oldest light directly observable in the universe. It is sometimes described as the afterglow of the Big Bang, but even that phrase can make it sound like a single lamp was burning somewhere far away. It was not a lamp. It was everywhere. For the first hundreds of thousands of years, the universe was hot and dense enough that light could not travel freely for very long. Free electrons were everywhere, and they scattered photons again and again. The cosmos was full of light, but it was also opaque, like a fog made not of water but of charged particles. Then the universe expanded and cooled. Around 380,000 years after the Big Bang, atomic nuclei could finally capture electrons and form neutral atoms. This period is called recombination. Once many electrons were bound into atoms, there were fewer free electrons to scatter light. The fog cleared. For the first time, light could travel for great distances. That released glow is still here. It has been stretched by the expansion of the universe from hot, early light into cold, microwaves, but it remains the oldest image we have. It is not a photograph of stars or galaxies. It is a photograph of the universe before stars and galaxies, a baby picture made of temperature differences so small that they became everything. This is where the language gets delicate. If there was already light, why do astronomers call the next era dark? The answer is that the cosmic microwave background was not local starlight. It was a fading background glow from the whole young universe. After it streamed free, there were no new bright objects inside the cosmos to replace it. As space expanded, that background light stretched and cooled. At visible wavelengths, the universe became dark. So the dark ages were not dark because photons did not exist. They were dark because no stars existed. No new furnaces. No galaxies. No bright points. No places where matter had become hot enough to ignite fusion and pour light into its surroundings. You can think of it like a room after a flash. For a moment the walls glow from the flash that has just happened. Then the glow fades. The room is not empty. Furniture may be there. Dust may be there. The air may be moving, but until someone lights a candle, there is no lamp inside the room. The cosmic microwave background is that fading flash. The first stars are the candles. But even candle is too small. The first stars were probably enormous. Theory predicts many of them were tens to hundreds of times the mass of the Sun. They were likely hotter, brighter, and shorter-lived than the stars that make the modern sky feel calm. They were not gentle yellow suns with planets. They were blue-white furnaces made from almost pure primordial fuel. This also means the first darkness was not only waiting for light, it was waiting for a different kind of light than the one most people imagine. The first starlight was not warm sunset light on a planet. There were no beaches to receive it, no clouds in an atmosphere, no mountains casting long shadows. It was radiation entering raw gas. It was physics changing the condition of space before there were worlds to make it beautiful in, the familiar sense. The beauty comes from knowing what it begins. But they could not exist immediately after recombination. The gas had to gather first. The universe had to expand, cool, and let gravity amplify the tiny differences already visible in the cosmic microwave background. Those differences are one reason the CMB is so important. It is not only old light. It is a map of future structure. The faint mottling in that background is the trace of unevenness. Slightly warmer and cooler patches, slightly denser and thinner regions, the small beginnings of all later clumping. In those small differences, the universe had already written a rough sketch of galaxies. Not a final map. Not a set of named constellations. A sketch. A whisper of where matter would eventually fall. For a sleep story, this can be one of the calmest ideas in cosmology. Nothing has to hurry. The early universe did not rush from darkness to a sky full of stars. Gravity worked in deep time. It pulled softly and continuously. It turned almost nothing into something, but only because it had time. And after the cosmic microwave background faded out of visible light, that patient process took over. The stage was transparent. The room was dark. The fuel was everywhere. The question was no longer whether light existed somewhere in the past. The question was where the first new light would be born. And the answer was not everywhere. That is another important soft correction. The universe did not become full of stars evenly, like a ceiling slowly filling with pinholes. The first stars would have formed only in the earliest dense regions, inside the first halos that crossed the right thresholds. Most of the cosmos remained dark, while a few rare places began to change. That brings us into the long dark room itself, the era when the universe had the ingredients of stars, but not yet the first flame. The Dark Ages are easy to misunderstand because the name sounds empty. It makes the era feel like a blank space between important events. But the Dark Ages were not blank. They were full of preparation. Imagine the universe after recombination, transparent, expanding, cooling, filled mostly with neutral hydrogen and helium. The cosmic microwave background is still present, but it is stretching and dimming. There are no stars, there are no galaxies. At visible wavelengths, if there were eyes to see, there would be nothing like the night sky we know. But gravity is awake. The invisible part of the story is dark matter. Dark matter does not shine. It does not gather into stars. It does not make familiar atoms. But it has gravity, and that gravity matters. In the early universe, dark matter began forming clumps and filaments earlier and more easily than ordinary gas could. Those clumps became the first scaffolding. Ordinary matter fell into that scaffolding. Hydrogen and helium did not choose their path, they followed the pull. This is one of the quietest transformations in the whole story. A sea of gas does not suddenly become a star, it gathers. It drifts into deeper regions. It compresses. It becomes uneven. It cools, then falls more. The centre grows denser. The outside keeps feeding it. At first, nothing shines. That is important. The universe can be doing extraordinary work without looking bright. For a long time the story is hidden in darkness because the work is gravitational, not luminous. There are no glowing nebulae yet because there are no stars to light them. There is no dust in the familiar sense because heavier elements have not been made by stars. There is only primordial gas and the dark matter valleys that give it places to collect. This is also why many artist impressions of cosmic dawn have to be treated as impressions. The real scene has no camera sitting outside it. No nearby star lights the cloud from the side. No colourful dust glows in red and gold. The colours used in visualizations are ways for modern minds to see structure, not literal views from a spacecraft. The truth is darker, quieter, and more difficult to photograph. But difficult does not mean unknowable. Modern astronomy can model this era, but seeing it directly is hard. Hydrogen in the early universe does leave possible signatures. The most famous is the 21 centimetre signal, a faint radio imprint connected to neutral hydrogen. Instruments such as Hera, EGES, and the Future Square Kilometre Array aim to use that signal to study cosmic dawn and reionization. But the signal is extremely faint. The sky at those radio frequencies is bright and noisy. Human radio interference can drown the measurement. The instruments must be placed in quiet places and calibrated with extreme care. Hera has set strong limits, but the 21 centimeter signal from cosmic dawn has not yet been definitively detected. Aegeus reported a famous absorption result that still needs independent confirmation. So for now, part of this era remains hidden. That uncertainty is not a weakness in the story. It is the story. The Dark Ages are a frontier because they sit between two kinds of evidence. On one side, the cosmic microwave background gives a detailed image of the universe at about 380,000 years. On the other side, JWST and other telescopes are now finding galaxies only a few 100 million years after the SIR beginning. Between those points is the room where first light happened. Not fully mapped. Not empty. Not silent in the mathematical sense, but still unlit. This is why cosmic dawn is so compelling. It is not a single sunrise. It is a transition from a universe with no discrete light sources to a universe filled with them. And transitions are where the deepest questions live. When did the first gas cloud become dense enough? How massive was the first star? Did it form alone or with siblings? How quickly did the first black holes appear? How fast did the first galaxies assemble? And how did the first stars change the material around them so completely that later stars, planets, and life became possible? The Dark Ages hold all of those questions quietly. In the script of the universe, this is not the empty page before the first chapter. It is the page where the ink is invisible until warned. The first light is already being prepared by gravity. The gas is already falling. The densest regions are already becoming more dense. And inside the deepest of those early clouds a new problem appears. Falling gas heats up. If it cannot cool, pressure fights gravity and the collapse slows. To make a star, the gas has to lose energy. It has to become dense enough for the center to grow hot, but not so pressure supported that collapse stops too soon. The universe needed a way for primordial gas to cool. It did not yet have dust grains. It did not yet have carbon monoxide clouds like modern star-forming regions. It did not have the rich chemistry of the Milky Way. It mostly had hydrogen and helium. Even that simple gas had a few tricks. Under the right conditions, some hydrogen could form molecular hydrogen, and molecular hydrogen can help gas lose energy. This mattered because without cooling, gas stays puffy and resists collapse. With cooling, a cloud can continue falling inward and concentrate more mass into a smaller region. So the first star was not made by gravity alone in the most general sense. It was made by gravity plus cooling. A fall has to become dense. Heat has to be carried away. The center has to keep contracting until the pressure and temperature cross the threshold where fusion becomes possible. So the first star did not form in the same kind of nursery as the sun. It formed in a simpler, stranger place. A cloud learned to fall. And in the next room of the story, that falling cloud begins to make the first furnace. A star is not a thing that appears. It is a thing that collapses into existence. The first star began as gas in a dark matter halo. A halo is not a shining object. It is a gravitational well, a deepening region where dark matter has gathered and ordinary gas can collect. In the young universe, these early halos were small compared with later galaxies, but they were enough to begin the work. Hydrogen fell inward. Helium came with it. The gas compressed, and compression made it hotter. That heat mattered because heat creates pressure. Pressure pushes outward. Gravity pulls inward. Every star is born from a negotiation between those two tendencies. Gravity wants collapse. Pressure resists. For collapse to continue, the gas must cool. In modern star-forming clouds, there are many cooling channels. Dust grains, heavier elements, and complex molecules help gas radiate energy away. But before the first stars, there were almost no heavy elements. There had been no earlier generations of stars to make them. The early gas was nearly pristine. That word, pristine, can sound beautiful. In astrophysics, it also means limited. Hydrogen and helium alone do not cool gas as efficiently as metal-enriched gas does. In astronomy, metals means elements heavier than helium. The first star-forming clouds had almost none of them. That likely changed the mass of the first stars. Because the gas could not fragment and cool in the same familiar way, the first stars may have grown very large. NASA's Webb resources summarize the theoretical expectation. The first stars may have been 30 to 300 times as massive as the Sun and millions of times brighter, burning only a few million years before exploding. This does not mean every first star had the same mass. It means the first generation was likely very different from the gentle, long-lived stars that now dominate much of cosmic history. The first stars were made from the universe's simplest fuel: hydrogen, helium, gravity, time. The scene is hard to picture because there is no familiar scenery yet, no rocky planets, no icy moons, no dust lanes blowing red in a telescope image, no golden sunrise over a horizon. A first star forms in a place where all later beauty is still only potential. Inside the gas cloud, the center grows denser. Matter falls in from all directions. As the core contracts, temperature rises. At first it is just heat from collapse. Then the pressure and temperature climb toward the threshold where nuclei can fuse. Hydrogen begins to become helium. Fusion starts to release energy from the center. A star is born when gravity's fall becomes a furnace. This is the physical answer to the episode's master question. Where did the first light come from? It came from gravity compressing primordial hydrogen until nuclear fusion began. That answer is simple, but it carries an enormous consequence. The first starlight did not arrive from outside the universe. It was made from the universe's own matter. Darkness did not need to be defeated by something foreign. It contained the ingredients of light from the beginning. This is the episode's quietest emotional turn. The first light was not an interruption, it was a consequence. If hydrogen gathers and cooling allows collapse, and gravity keeps working, and the center becomes hot enough, darkness produces a star by following its own rules. The first morning was not imported into the universe. It grew there. But there is another detail. The first star was not only a light source, it was also a chemical machine. In its core, it began turning hydrogen into helium. In later stages, depending on mass, stars can build heavier elements. And when the most massive stars die, they can throw enriched material back into space. Before the first stars, There was no oxygen drifting through galaxies the way we understand oxygen now. There was no carbon for life, no silicon for rock, no iron for planetary cores. The periodic table was barely started. After the first stars, the universe could begin changing its recipe. That is why the first star matters more than a lamp. It is the first local light. It is the first major ultraviolet engine. It is the first step toward heavy elements. It is the beginning of the long chemical road that eventually makes dust, planets, atmospheres, water, and bodies that can look back. In a sleep story, this can be held softly. There was a time when the universe had no way to make an ocean. Then the first clouds fell. The first stars burned. The first stars died. And in dying, they gave the next stars more to work with. But first, before any of that ash could spread, the very first furnace had to open its eyes. The next part is the moment the Dark Ages begin to end. Not everywhere. Not all at once. Just in one small region where the first star turns on. The first star did not light the whole universe. It lit a neighborhood. That is the right scale to hold in mind. Cosmic dawn was not a switch flipped across all of space. It was a set of small beginnings. A star here, a cluster there, a young galaxy somewhere else. Around each source, light began changing the gas nearby. Far away, darkness remained. So the first star's first light was local. It was also intense. A massive primordial star would have poured out ultraviolet radiation. Its surface would have been hot and blue-white. It would have burned fuel at a furious rate compared with smaller stars. If it had no heavy elements, its structure and light would differ from familiar stars. In modern terms, such a star would not be comforting up close. It would be too bright, too hot, too short-lived. But at cosmic scale, it is gentle in another way. Gentle because it is the first small answer to a vast darkness. One point, one bubble, one region changed. The universe did not need 1,000,000 galaxies to begin cosmic dawn. It needed the first successful furnace. There were no planets around it in the way we imagine planets now. There had not been time or ingredients to build rocky worlds. No dust disk full of metals. No quiet system waiting for life. The first star was not a home. It was a beginning. Its ultraviolet light hit the neutral hydrogen around it. Enough energy can remove electrons from hydrogen atoms, turning neutral hydrogen into ionized gas. In this way, the first stars began making bubbles in the cosmic fog. That word, fog, needs care. It was not fog like mist over a field. It was hydrogen spread between early structures, capable of absorbing and scattering some forms of light. In the Dark Ages, this neutral hydrogen made it difficult to see the earliest sources directly. As the first stars and galaxies formed, their energetic radiation began ionizing the hydrogen around them, making space more transparent in growing patches. A bubble opened. Inside the bubble, light could travel differently. Outside the bubble, the old darkness remained. That is a beautiful image, because it is not dramatic in the usual way. There is no battle, no explosion yet, no cosmic thunder, just a young star sending light into gas that has never been lit from within before. The first star was probably short-lived. Massive stars live fast because their cores run hotter and consume fuel more quickly. A star many times the mass of the Sun may burn for only millions of years, not billions. In cosmic time, that is a candle flash. But it is a candle flash that changes everything nearby. The light begins reionization. The heat changes the gas. The radiation can affect whether nearby gas collapses or resists collapse. And when the star dies, if it is massive enough, it can seed the surrounding universe with the first heavier elements. This is one of the deepest so-but turns in the story. The first stars were needed to make later stars richer. But because they were so massive, many of them may have died quickly. So the first light did not last as a steady, gentle era at first. It flickered, it appeared in bubbles, it died, it left traces, then new stars formed from changed material. The universe learned to shine through repetition. A first star. Then its death. Then enriched gas. Then more stars. Then larger groups. Then galaxies. At the beginning there may have been only isolated points of fire in an enormous dark field, but each point made the next point easier in some ways and harder in others. Radiation heated and pushed gas, supernovae disturbed clouds, heavy elements cooled future gas more efficiently. Black holes may have formed from some remnants and begun shining as they fed. Cosmic dawn is not a gentle sunrise over a flat horizon. It is a scattered awakening. Little islands of light appear in a sea of hydrogen. Some islands fade. Some merge. Some grow into galaxies. And the first stars themselves become almost impossible to catch directly because they live so early, so briefly, and so far away. This is why JWST's current discoveries matter so much. If the first stars are difficult to see directly, astronomers look for their effects. They look for early galaxies that already shine brightly. They look for signs of chemical enrichment. They look for helium emission without metals. They look for ionized bubbles in a universe that should still be mostly fog. They look for light that seems to have arrived too early. The first star turns on, but we may never see that exact star. We may see the room after it lit it. We may see the ash. We may see the next generation. We may see the fog beginning to tear. This is why the story must move carefully from imagination to evidence. It is fair to picture a first star because the physics calls for one. It is not fair to pretend the image is an observation. The observation is usually later. A galaxy, a chemical signature, a spectrum, a hydrogen signal, or a candidate fits theoretical expectations. And that tearing is the next part of the journey. The first stars had a strange gift. They could not keep their light for long, but they could give the universe new ingredients. In modern astronomy, a star's death can be as important as its life. A star shines by fusion, but its final stages can create, release, or distribute heavier elements. Massive stars can end as supernovae, throwing material outward into space. Some may collapse into black holes. Some may leave neutron star-like remnants depending on mass and physics. For the first generation, the details are still an active field of research. But the broad consequence is clear. Before stars, the universe was mostly hydrogen and helium. After stars, the universe could become chemically richer. This is the beginning of the road to oxygen, and carbon, and silicon, and iron, and the dust that later helps gas clouds cool and fragment into smaller stars. The first enrichment would have been uneven. One region might receive the ashes of a massive star, while another region, far away, remained nearly pristine. Some clouds would be changed early. Others would keep forming stars from simpler gas. Cosmic dawn was not one clean layer spread across the universe. It was patchy, local, and complicated. That patchiness is useful. It means the early universe could contain both very primitive regions and surprisingly mature galaxies at the same broad era. It gives astronomers a reason to expect variety instead of one uniform dawn. The first stars did not create all of that at once in every place, but they began the process. Their deaths seeded surrounding regions. The next clouds inherited a changed recipe. This is a powerful sleep-soft idea because it turns destruction into preparation. The first star burns. The first star dies. The darkness receives ashes, and those ashes make later light possible in a different way. Without heavy elements, star formation is less efficient at making small, long-lived stars like the Sun. With heavier elements and dust, gas can cool in new ways. It can break into smaller pieces. It can make stars that live for billions of years. It can make disks where planets form. The first stars may have been too massive and brief to host anything like a home. But they made the idea of home more possible. That is the emotional spine of Part 6. The first light was not the light we live under. It was the light that made later lights possible. There is another thread too: black holes. Some of the first massive stars may have collapsed into black holes. Those early black holes could feed on gas, shine in high-energy light, and help heat the hydrogen between galaxies. NASA's early universe resources note that black holes could have grown and merged into the huge black holes now found in the centers of massive galaxies. This does not mean the first stars instantly made quasars everywhere. It means the first stellar deaths may have planted seeds for another kind of early light. Starlight. Supernova light. Accretion light from black holes. Together these sources help transform the young universe. In a dark room, one candle changes only a small area. But many candles, over time, change the whole room. Cosmic dawn worked this way. The earliest stars and galaxies did not simply add dots of light. They altered the medium that light had to cross. They began ionizing neutral hydrogen. They enriched gas. They created remnants. They changed cooling. They created feedback, a word that sounds technical but means the universe began reacting to its own first lights. A star forms because gas falls. The star's light heats and pushes the gas. The star dies and throws material outward. That material helps or hinders future star formation depending on where it goes and what it does. So the universe is no longer only falling. It is responding. That is the difference between the Dark Ages and cosmic dawn. During the Dark Ages, gravity quietly gathers. During cosmic dawn, light begins pushing back. The first stars are gone now if they existed as theory predicts. They burned out more than 13 billion years ago. Their photons have stretched. Their remnants have changed. Their ashes have been folded into later generations. But the effects of those stars remain. Every oxygen atom has a stellar history. Every carbon atom has a stellar history. The iron in a planet's core, the silicon in rock, the oxygen in water, all belong to the long chemical story that first stars began. This is why the ALMA oxygen detection in JDA's GS 14-0 matters later in the episode. Oxygen in a galaxy seen less than 300 million years after the Big Bang means stars had already lived and died there or nearby quickly enough to enrich the gas. It is not only a chemical detail. It is a clock. It also changes the feeling of the early galaxy. A galaxy with oxygen is not only a knot of first gas, it has a past. However brief that past is, it contains stellar life cycles. It contains transformation. It contains at least some earlier fire. It tells astronomers that the first rounds of star formation must have started earlier than the oxygen itself. The evidence is like finding warm ash in a room and knowing a fire has already burned. You may not have seen the first flame, but the ash tells you it was there. And once enough flames appear, the fog itself begins to change. That is the next step. The dark room starts becoming transparent. Reionization is a cold word for a beautiful change. It is the era when the universe's neutral hydrogen was ionized again by the light from the first stars, galaxies, and perhaps early black holes. The word looks technical because it is technical, but the image is simple. The young universe was filled with a kind of hydrogen fog. Then the first luminous sources began making holes in it. At first, those holes were small. Around a massive star, a bubble. Around a young galaxy, a larger bubble. As more stars formed, more bubbles appeared. As galaxies grew, bubbles expanded and overlapped. Eventually, much of the intergalactic hydrogen became ionized, and the universe became more transparent to the kinds of light astronomers use to study distant galaxies. This process was not neat from the inside. Some regions were ionized early because they had clusters of young stars. Other regions remained neutral for longer. If someone could map it from outside, it would not look like a single wall rolling forward. It would look like bubbles, islands, and tunnels growing until they touched. That is why astronomers talk about the topology of reionization, not only when it happened, but what shape it had. NASA describes this epoch as running from the end of the Dark Ages to when the universe was, around 1 billion years old. Max Planck research places the end of reionization around 1.1 billion years after the Big Bang. The exact start is still uncertain. That uncertainty is important. The first stars did not leave a simple timestamp. Cosmic dawn is not one date. It is a process. This is why different instruments search in different ways. JWST sees early galaxies directly through infrared light, catching light that has been stretched by expansion. ALMA can observe emissions from elements such as oxygen in extreme early galaxies. radio arrays look for the 21 centimeter hydrogen signal, which could map how neutral hydrogen changed before and during reionization. Each method sees a different layer. JWST sees the lamps. ALMA can detect some of the changed chemistry. HERA, IGES and the future SKA try to hear the gas between the lamps. Together they turn cosmic dawn from a single question into a layered investigation. One instrument asks where the early galaxies are. Another asks what elements they contain. Another asks what the hydrogen between them was doing. None of those views is complete alone, but each one removes a little more darkness from the map. That phrase, "hear the gas," is not literal sound in space, but for a sleep video it is a useful feeling. The 21 centimeter signal is a radio signature. It is not a pretty galaxy image. It is more like a faint record of hydrogen's state, whether it was colder or warmer than the background radiation, whether it was neutral or ionized, whether the first stars and black holes had begun altering it. MIT's HERA work describes how the 21 centimeter signal could tell researchers what galaxies were doing even when the galaxies themselves were too faint to see. HERA has not definitively detected the cosmic dawn 21 centimeter signal, but it has set limits that narrow possible models. EGES is another instrument in this story. Its 2018 absorption result was famous because it suggested a signal from the birth of the first stars, but the project itself notes that the result requires independent confirmation. So the radio part of Cosmic Dawn remains careful. Not solved. Not empty. Careful. That care is part of the identity of the slow cosmos. The episode can hold mystery without pretending everything is known. The real universe is more interesting than a fake certainty. Here is what can be said firmly. The first stars and galaxies began changing neutral hydrogen. The universe moved from dark ages into cosmic dawn. The process took hundreds of millions of years. By around 1 billion years after the Big Bang, reionization was largely complete. What remains uncertain is the exact timeline, the relative contribution of small galaxies, massive stars, black holes, and other sources, and the physical details of how quickly the first structures form. This uncertainty creates a strong part ending. Because when Webb began looking deeply enough, it did not find a slow, empty dawn waiting politely at the edge of models. It found bright galaxies. It found compact galaxies. It found galaxies with signs of surprisingly fast growth. It found a universe already making structure when it was only a few % of its current age. The fog had not only begun to tear. In some places, it may already have had bright holes in it. And one of the newest examples is so far back that its light has been travelling for nearly the whole history of the universe. This is where James Webb enters the room. Not as the maker of the first light, as the instrument now catching its aftermath. James Webb sees old light by looking in infrared. That is the simple version. The more precise version is that the expansion of the universe stretches the wavelengths of light travelling across cosmic time. Light that began as ultraviolet or visible can arrive at Webb as infrared. This stretching is called redshift. The higher the redshift in general, the farther back in time astronomers are looking. At these distances, pictures alone are not enough. A red smudge can be a candidate. But spectroscopy is how astronomers confirm what they are seeing. Spectroscopy spreads light out and looks for features that reveal redshift, chemistry, and physical conditions. NASA's MOMS 14 article emphasizes why this matters. Images can estimate distance, but detailed spectroscopy confirms when the light was emitted. This brings us to MOMS 14. In January 2026, NASA reported that JWST confirmed a bright galaxy called MOMS 14 at redshift 14.44. Webb saw it as it appeared only about 280 million years after the Big Bang. Its light has been travelling through expanding space for about 13.5 billion years. That is difficult to hold in ordinary thought. The universe is about 13.8 billion years old. MOMS 14 is not nearby in the way a star is nearby. It is not even nearby in the way Andromeda is nearby. It is a message from near the beginning of galaxy formation. There is also a useful humility in the word near. 280 million years after the Big Bang is not the first instant. It is not even the first million years. A great deal can happen in 280 million years if the environments are dense and the processes efficient. The surprise is not that anything exists. The surprise is how bright, numerous, and chemically suggestive some of these early systems appear. The source paper calls it a remarkably luminous galaxy at specs Expo 14.44, confirmed with JWST. It describes a sharp Lyman alpha break, rest ultraviolet emission lines, compact size, young stellar population, and a number density of bright Z equals 14 to 15 sources more than 100 times larger than pre-JWST consensus models expected. The exact technical language can be left to the paper, but the story meaning is clear. Spectra turn a faint red speck into a timed message. They let astronomers say not only there is something red there, but this light belongs to galaxy at a specific early epoch. That is the difference between a candidate and a confirm chapter in the timeline. For a general viewer, the exact numbers matter less than the shape of the surprise. Webb is finding bright early galaxies where many models expected fewer, fainter, simpler systems. This does not mean the Big Bang is wrong. It does not mean astronomy is broken. It means early galaxy formation may have been faster, more efficient, more bursty, or more chemically unusual than the pre-Webb picture allowed. That is already enough. It means the first light was not a slow decorative fade-in. It may have been a rapid, uneven, intense beginning. MOMS 14 also shows unusual nitrogen enrichment, according to NASA's report. The NASA article notes that there may not have been enough time for ordinary generations of stars to produce such high amounts of nitrogen in the usual way, and one idea is that dense early environments produce supermassive stars unlike stars observed in the local universe. Again, careful language matters. This is not a final verdict. It is a clue. But clues are how cosmic dawn is reconstructed. A galaxy only 280 million years after the Big Bang is not the first star itself. It is already a system. It already contains stars. It may already have a history of star formation inside it. If it is chemically unusual, that history may include stars that lived and died even earlier. So Webb is not just seeing an object. It is seeing a consequence. and consequences point backward. MOMS 14 is not alone in changing the picture. Before it, Jade's GS 14-0 became a record-breaking galaxy observed when the universe was less than 300 million years old. NASA's Webb reporting described an unambiguous redshift of 14.32 from NISPEC observations. ESA/Webb image releases placed it about 290 million years after the Big Bang. Then ALMA added a different kind of clue. Oxygen. Not oxygen in a nearby nebula. Oxygen in one of the most distant confirmed galaxies. Oxygen is a heavier element. It is made by stars and spread when stars die. Finding it so early suggests that star formation and chemical enrichment had already happened, rapidly. This is where the title becomes honest. James Webb found light too early in the universe. Not because light was impossible, not because physics has failed, because the old comfortable expectation of how rare and simple bright early galaxies should be has been strained by the data. Webb keeps pushing the edge back. Hubble found GNZ 11 at about 400 million years after the Big Bang. Webb confirmed and surpassed earlier records. Jade's GS 14 pushed to less than 300 million years. MOMS 14 pushed to about 280 million years with spectroscopic confirmation. Each step gets closer to the room we cannot yet see clearly. The room where the first stars formed. A telescope cannot make the universe younger. It can only make our view deeper. And the deeper view is telling astronomers that by the time Webb sees these galaxies, the first acts may already be over. The lamps are on. The fog is being cleared. The chemistry has begun. And now we need to ask what kind of dawn could grow up so quickly. That question leads to one galaxy that seems too mature for its age, because in its light, astronomers found an element that should have required earlier stars. Oxygen is ordinary to us. That can make it hard to feel how strange it is in the early universe. We breathe it, we find it in water, we find it in rock. It is one of the elements that makes Earth feel familiar. But oxygen is not primordial in the same way hydrogen and helium are primordial. The early universe made hydrogen and helium with tiny traces of a few light elements. Oxygen had to wait for stars. Stars make heavier elements through fusion and stellar evolution. Massive stars can spread those elements through winds and supernovae. Later generations of gas clouds inherit that enrichment. Over time, galaxies become chemically mature. So when ALMA detected oxygen in Jade's GS 14-0, the result mattered. ESO described Jade's GS 14-0 as the most distant confirmed galaxy known at the time, seen when the universe was less than 300 million years old, about 2% of its present age. The oxygen detection suggested the galaxy was much more chemically mature than expected. ESO reported that the galaxy had about 10 times more heavy elements than expected. This is the kind of fact that can be told gently but still carry tension. A galaxy less than 300 million years after the Big Bang should be young. And it is young. But it already carries signs that stars have lived, made oxygen, and enriched their surroundings. That means the story began earlier than the observation. If you find ash, the fire happened before you arrived. If you find oxygen in an early galaxy, stars had already been at work before the light you are seeing left that galaxy. This does not tell us the exact identity of the first stars. It does not tell us the exact first morning. But it pulls the timeline tight. There is only so much time between the Big Bang and a galaxy observed at less than 300 million years. In that interval, gas had to gather, stars had to form, some stars had to die or enrich their environment, and a galaxy had to become bright enough for Webb and Alma to study across cosmic time. That is why early oxygen feels like a clock. It does not tick with seconds. It ticks with stellar generations. To make oxygen, the universe needs stars. To distribute oxygen, some stars must die or shed material. To detect oxygen in a galaxy at this age, the enrichment must have happened fast. Astronomers are now trying to understand how. Maybe star formation in early galaxies was bursty and intense. Maybe galaxies were more efficient at turning gas into stars than expected. Maybe dense early environments created unusual stars. Maybe the first galaxies were small but bright in ways pre-Webb models underestimated. Maybe some sources include active black holes, though the MOMSIS 14 paper notes its features suggest an active galactic nucleus is not the dominant source of ultraviolet light. The important thing for the episode is not to pretend to settle those debates. The important thing is to let the viewer feel the clock. There was darkness. Then gravity made clouds. Then stars ignited. Then some stars died. Then galaxies became chemically enriched. And Webb is already seeing galaxies where that sequence has begun astonishingly early. This is why Befn Stars works as a thumbnail caption, even though the video title says light. The deepest curiosity is not only what Webb sees. It is what had to exist before Webb's galaxies could shine the way they do. Before the oxygen, there had to be stars. Before the stars, there had to be collapsing clouds. Before the clouds, there had to be tiny density differences. Before the galaxies, there had to be dark matter wells. The visible clue points into the invisible past. There is another reason oxygen is emotionally useful. It connects the first light to us. Oxygen is not just an astronomy word. It is part of the ordinary body, ordinary water, ordinary stone. In a sleep documentary, this lets the cosmic scale come home without becoming sentimental. The oxygen in a distant galaxy less than 300 million years after the Big Bang is not the oxygen in your room, but it tells the same broader story. The universe began making the elements of later worlds, very early. The first stars did not know they were preparing oceans, but chemically they were. The first galaxies did not know they were preparing planets, but materially they were. Every later calm thing depends on earlier violent stars. That is one of the quiet truths of astronomy. Peaceful worlds are made from old fire. Still, there is a limit to what these oxygen detections and early galaxies can tell us. They show that first stars or early stellar populations must have existed before them. They show that enrichment happened quickly. They show that early galaxies can be brighter and more complex than expected. but they do not show us the first star directly. The first star itself remains hidden. And that is where the next part goes, into the difference between seeing the first light, seeing its traces, and seeing candidates that may finally belong to the first generation. The most honest sentence in this episode may be the first sentence of the hook. James Webb has not photographed the first star. That matters. It would be easy to make the story louder than the science. It would be easy to say that Webb has finally seen the first stars, or that astronomers have solved cosmic dawn, or that the universe has been rewritten completely. But the real frontier is more careful. The first generation of stars is called Population 3. The name is historical and a little backwards. Population I stars are metal-rich stars like the Sun. Population 2 stars are older and metal-poor. Population 3 stars would be the first, made from primordial gas before previous stars had enriched it. Population 3 stars are expected to be metal-free or nearly metal-free, because there were no earlier stars to make heavier elements. They are expected in many models to be massive, hot, and short-lived. They are expected to have helped start reionization and chemical enrichment. But directly detecting them is hard. They formed extremely early. They may have lived briefly. They may have been embedded in small faint systems. They are far beyond ordinary reach. So astronomers look for signatures. One possible signature is helium emission without metal lines, because extremely hot primordial stars can produce hard radiation capable of ionizing helium. A 2026 ArXiv paper reports confirmation of a Hei 1640 emitter near GNZ11 at redshift 10.6, with no metal lines detected. The authors say population 3 stars are the most plausible explanation, while direct collapse black hole or primordial black hole scenarios cannot be fully ruled out. That is exactly the kind of language the script should keep. Most plausible explanation, not final proof. Another candidate is LAP-PORN B. A 2025 paper argues it is the first observed system consistent with several theoretical predictions for population 3 stars. It is gravitationally lensed, meaning a foreground mass helps magnify it. The paper places it in a small dark matter halo and argues it matches expectations for low mass, clusters of massive POP3 stars. Again, this is a candidate. A possible clue. Not a clean photograph of the first star turning on. NASA has also discussed galaxies that may be missing links to the first stars. In one case, Galaxy 9422 around 1 billion years after the Big Bang showed exotic conditions, but NASA quoted researchers saying it does not have population 3 stars because the data show too much chemical complexity. Instead, it may help explain the transition from primordial stars to more familiar galaxies. That is an important distinction. Some galaxies are not first star systems themselves, but they are windows into the transition after first stars. The closer astronomers get, the more the story becomes a set of traces. No metals here. Too much oxygen there. A helium line. A redshift. A young compact galaxy. A bubble of ionized gas. A possible 21 centimeter signal. Each clue is a footprint in a room where the first flame has already moved on. This can be told gently because uncertainty is not a failure. In sleep content there is no need to force a hard conclusion. The viewer is allowed to rest inside the unknown. The unknown here is beautiful. We are close enough to see the smoke, close enough to see the ash, close enough to see later fires burning in rooms the first fire prepared. But the first flame itself is still just beyond the doorway. That doorway is moving. Webb has moved it. Alma has sharpened some distances and chemical measurements. Hera and Ska class radio work may eventually map hydrogen through the dark ages, and reionization more directly. Future deep fields may find more galaxies at redshift 14 and beyond. NASA's Roman Space Telescope, with its wide infrared view, may increase the sample of early bright galaxies dramatically. Larger samples matter because one strange galaxy can be an exception, but many strange galaxies become a new pattern. And this is where the title's tension resolves. James Webb found light too early in the universe because the universe was already forming bright galaxies near cosmic dawn. But too early does not mean impossible. It means earlier than expected by the older, comfortable picture. It means models must learn from observations. It means the first stars may have formed, died, enriched gas, and helped build galaxies with startling speed. It means cosmic dawn may have been less like a slow dimmer switch and more like scattered fires, appearing quickly across deep night. Still, the episode cannot end with Webb alone, because the first light matters not only as a telescope problem. It matters because it changed what the universe could become. The first stars did not simply end darkness. They opened the route to later galaxies, later suns, later planets, and eventually the quiet observer listening to this story in a dark room. That is where part 11 goes, from the first light as evidence to the first light as inheritance. The first light did not make us immediately. It made us possible. That is the right scale. Between the first star and a sleeping room on Earth lie more than 13 billion years of cosmic history. Galaxies had to grow, stars had to be born and die. The Milky Way had to assemble from mergers, gas flows, star clusters, and dark matter. The Sun had to form from gas already enriched by elder stars. Earth had to gather from a disk of dust and rock. Life had to arise much later. But the chain begins with the first generation of stars changing the universe's ingredients. Before first light, there is hydrogen, helium, gravity, dark matter, radiation, and time. After first light, there is feedback. There is ultraviolet radiation. There are ionized bubbles. There are supernovae. There are black hole seeds. There are heavier elements. There is chemistry becoming richer. There is a path toward the kind of star formation that can make long-lived stars and planetary systems. This is why the first stars are not only an origin story for astronomy, they are an origin story for complexity. The universe after first light is no longer the same as the universe before it. It has begun making its own future. A calm way to picture it is to imagine the Milky Way as a memory palace. Every old star in its halo remembers earlier star formation. Every metal poor star is a fossil of a younger chemical universe. Every atom heavier than helium points back to stellar work. Some of the most ancient stars in our own galaxy are like local archaeology. NASA's MOMSES 14 article even draws a comparison between unusual nitrogen in early galaxies and ancient stars in the Milky Way that may preserve abundance patterns from the early universe. The farthest galaxies and the oldest local stars are two ends of the same investigation. One looks outward and backward. The other looks nearby and ancient. Together, they ask what the first stars were like. This gives EP6 a natural seed after the first light. Our own galaxy becomes a fossil record of that light. The Milky Way is not just a spiral in the night sky. It is a layered memory of stars that lived before the Sun. But tonight, we stay with cosmic dawn. We stay with the moment before there were familiar galaxies. We stay with the first transformation. The early dark was not an enemy. It was the condition that made the first light meaningful. It held the fuel. It held the density ripples. It held the dark matter valleys. It held the waiting. When the first stars turned on, they did not erase the dark all at once. They made islands. Around each island, gas changed. More islands followed. Galaxies gathered. The fog thinned. The universe became increasingly transparent. Light crossed greater distances. And eventually, much later, a planet formed around a quiet star in a spiral galaxy, and minds on that planet built telescopes to look back toward the first morning. There is a loop closing here. The first stars made the later elements. The later elements made mirrors, detectors, computers, and eyes. Those eyes built James Webb. James Webb now looks back toward the era that made eyes possible. That is not a mystical claim. It is a material one. The universe used stars to make the things that study stars. In the slow cosmos register, this is not a reason to wake the viewer up. It is a reason to let the scale settle. The room is dark. The screen is dim. The voice is slow. And somewhere in the background of every ordinary night is an old fact. Darkness came first, but light was waiting inside it as gravity, gas, and time. The first star did not know anything. It did not aim. It did not intend to make later worlds. It simply burned because physics allowed it to burn. But after it burned, the universe was changed. This is the deepest resolution of the episode. Where did the first light come from? From hydrogen falling into darkness until the center became hot enough for fusion. Why does Webb find light so early? Because by the time we can see those galaxies, earlier stars have already done hidden work. What did first light change? Almost everything that came after. The last part can now slow down. The evidence has been paid off. The evidence has been answered. The open loops have closed carefully, without pretending certainty where science still has frontier. Now the episode can return to sleep. Not by leaving the subject, by resting inside it. The oldest morning happened without witness, but its light is still arriving. there is a quiet comfort in the fact that no one saw the first sunrise. No one needed to. The universe did not wait for a witness before it began. A cloud fell inward. A centre grew hot. Hydrogen fused into helium. Light pressed outward from the core of the first star and moved into gas that had never been, lit from within. A small bubble opened in the dark. Far away, the rest of the universe remained night. Then more lights appeared. Some died quickly. Some left black holes. Some threw heavy elements into space. Some helped build the next generation. The Dark Ages ended not as a single sunrise, but as many small mornings scattered across a vast field. That is the image to keep as the episode settles. Not a bright universe, all at once. A young universe, learning to shine. Here, the last light journey and the first light journey meet each other. At the far end, we imagine the universe after the stars are gone. At the near beginning, we imagine the universe before the stars arrive. Between those two darknesses is the age of light. The age that contains galaxies, planets, oceans, sleeping rooms, and the simple act of looking up. We live inside that age. Not at its beginning. Not at its end. Inside it. The first stars are gone, but their consequences remain. The early galaxies Webb sees are not the whole answer, but they are real clues. MORMS 14, JADES GS DUS 14, of oxygen at less than 300 million years possible, population 3 signatures, hydrogen radio searches still waiting for certainty. All of these are pieces of the same old morning. The honest picture is not finished. It is better because it is not finished. The universe is still being read. Webb has opened pages that older telescopes could not reach. ALMA has added chemical notes in the margin. Radio arrays are still listening for the faint hydrogen line that may one day map the dark room. Itself, future surveys may find thousands of early galaxies and show whether today's surprises are rare, jewels or the normal dawn. For now, the story is enough. The dark was real. The first light was real. The path from one to the other was gravity, gas, cooling, collapse, fusion, radiation, death, enrichment, and time. And in the end, the first light did not only illuminate the dark, it began the making of a universe that could remember. So let the picture soften. The first star is no longer a scientific diagram. It is a small point in a quiet black field. Around it, hydrogen glows. Beyond it, the universe is still dark. But the dark has changed. It has learned that light is possible. One day, much later, that possibility becomes galaxies. One day, it becomes the Milky Way. One day, it becomes the sun. One day, it becomes a night sky above a sleeping planet. And one day, it becomes a telescope looking back, trying to find the first trace of the morning that made the telescope possible. That is where we can leave the universe for tonight. Not at the end. Not at the beginning. At the moment the first light begins moving through the dark, and next time we can stay closer to home, inside the galaxy that still carries fossils of that first light, the Milky Way, a quiet spiral made from older fires. For now, rest. The oldest morning is behind us. Its light is still on the way, and the dark outside your window is not empty. It is full of old stars, old ash, and the long memory of the first blow.
you.